So this is the beginning of our last video, video number 4 for the cell signaling chapter. And in this video, we're going to discuss the role of ion channel linked receptors in neurons, specifically how ion channel linked receptors play a role in the action potential. So to understand the role of ion channel linked receptors, I first want to take a step back and think about how neurons communicate with one another. Here we see a picture of a neuron, and you can see that there's one major cell body, so this is where the nucleus would be located, along with many of the major organelles, the Golgi and other organelles. But we see many of these string-like processes that come out from the neuron. So neurons send out these processes or extensions in order to communicate with one another. And here you can see a schematic of two neurons that can communicate with one another. And in general, processes where neurons receive inputs are called dendrites. Then they propagate that signal down the axon, and then neurons connect with another neuron at regions called synapses, which we've already defined when we talked about synaptic signaling. Then this neuron can receive those inputs and then propagate the signal onto the next neuron. So what we're going to be focusing on here is at the synapse, if we were to zoom in. So for the neuron that is sending the signal, that neuron has many tiny vesicles at the nerve terminal. Those vesicles are full of neurotransmitters that can be released, and then they diffuse across the synapse where they activate the next neuron to continue propagating the signal. And so what we're going to be focusing on is when this neurotransmitter diffuses across and binds its receptor, what does that receptor do? And those receptors are ion channel linked receptors. So that's going to be our focus. So let's zoom in and consider that a little more. So here, if we look at the synapse, we can see at the presynaptic terminal, so this is the neuron that's sending the signal, we see lots of these dense vesicles that contain many, many neurotransmitters. And those neurotransmitters are going to be released in this tiny space between the neurons. This is the synapse. And then those neurotransmitters are going to bind receptors present on the postsynaptic side, or the receiving neuron. So here we can see that again in this schematic. So here we have our vesicles full of neurotransmitters. Those vesicles are then fusing with the membrane at the synapse to release the neurotransmitters. Then those neurotransmitters bind their receptors on the postsynaptic side, so the receiving neuron. And these receptors are ion channel linked receptors. So the focus of this video, we're going to start by talking about these ion channel linked receptors. And here you can see it one more time, that when this red neurotransmitter binds, it opens a gate that allows ions to flow freely through down their concentration gradient. So this is an example of passive transport. So these ions are going to flow down their concentration gradient and into or out of the neuron. So the key thing to remember here is that the role of neurotransmitters is that they serve as ligands to open these ion channel receptors. So when the neurotransmitter binds, it opens the gate, allowing ions to flow down their concentration gradient. So let's look at that a little more closely. So here you can see that under circumstances when we don't have our neurotransmitter bound, our gate is closed, so no ions can flow through. However, when the neurotransmitter binds, that opens the gate for this ion channel, and ions can then flow down their concentration gradient. This is an example of facilitated diffusion, which is a type of passive transport. So these molecules, these ions, are going to flow down their concentration gradient from an area of high concentration to an area of low concentration, which, as you remember, passive transport releases energy. So this is actually an exergonic process. And then when the neurotransmitter is no longer bound, the gate closes and transport ceases. So now let's take a step back again and let's talk about the neuron more broadly. So what I want you to think about is, imagine that this is the axon. So we're sending the signal down the axon to get it to the next neuron. So if we were to zoom in on this axon, what we would see is that outside the neuron, the charge is relatively positive compared to inside the neuron, which is relatively negative. So there is a charge differential across this neuron. This creates an electrical gradient across the neuronal membrane. In addition, we also have concentration gradients. So there's more potassium inside the neuron than outside. So the concentration of potassium is higher inside, and the concentration of sodium is higher outside. Therefore, passive transport of these ions is going to drive sodium inward and potassium outward. So if a voltage-gated potassium channel were to open, then potassium would want to move outward through this channel, whereas a sodium channel, when it opens, sodium would want to move inward through this channel. And just to remind you from the last chapter, in the last chapter we talked about the sodium-potassium pump. So hopefully you remember that the sodium-potassium pump is an example of active transport. This is a pump that uses energy from ATP to pump sodium out and potassium in, and that's actually what maintains this sodium-potassium gradient, where the level of sodium is higher on the outside and the level of potassium is higher on the inside. The resting potential of this neuron that's maintained by the sodium-potassium pump, it's approximately negative 70 millivolts because it's more negative on the inside than the outside. So now let's see what happens when we send a signal down the neuron. So we have three different ion channels that I want to talk about here. So first, we have our ion channel linked receptor. And in this case, we're going to use the acetylcholine receptor, or the ACH receptor, as an example. This is just an example of an ion channel linked receptor that binds the ligand ACH, or acetylcholine, and that's what drives it to open. The other two channels we have here, these are voltage-gated channels. So we have one voltage-gated sodium channel. This channel opens when the voltage reaches around negative 50 millivolts. Remember, the resting potential was negative 70 millivolts. This is a voltage-gated potassium channel, and this channel will open when the voltage reaches around plus 20 millivolts. So opening of these channels is driven by a change in potential. When acetylcholine binds the acetylcholine receptor, that is going to open a gate that's going to allow sodium to flow down its concentration gradient into the neuron. So then if we were to use an electrode to measure the potential in the neuron, that neuron that started out at negative 70 millivolts, well, now more and more positive charges are coming in. So it's making that neuron more and more positive on the inside. So this is called depolarizing the neuron. It's making it more and more positive. When it reaches negative 50 millivolts, this is the threshold potential. So at this potential, this is going to trigger opening of our voltage-gated sodium channel. So now our voltage-gated sodium channel opens and we have even more sodium rushing in. So now that potential, because we're letting more and more of those positive charges go in, it continues to depolarize, making that neuron more and more positive on the inside. So as we approach a potential of plus 20 millivolts, this is the threshold potential that allows opening of the potassium channel. So at this point, the potassium channel begins to open, and remember that the concentration of potassium is higher on the inside than on the outside. So potassium is going to flow outward. So that's moving positive charges back out of the neuron. So this starts to repolarize the neuron, bringing that potential back down towards where it was. So potassium is going to flow outward, bringing the potential back down. So here you can see the potential is moving back down, and it continues going down until it actually dips below negative 70 millivolts. And there are some additional channels here that help to reset the neuron after this hyperpolarization phase. We're not going to discuss them in this class, but you will learn about them in physiology. But then once we reach this resting potential, our sodium-potassium pump maintains the resting potential again. So this is how the action potential is generated. So just to review, during the action potential, so our stimulus is release of a neurotransmitter that opens an ion channel linked receptor like the acetylcholine receptor. Then our voltage-gated sodium channel opens, allowing sodium to continue to flow in, leading to this period of depolarization. At the peak, the voltage-gated potassium channel opens, potassium flows out, leading to repolarization. We have a brief period where the cell overshoots, that's this hyperpolarization, but once the resting potential is reset, it's maintained by the sodium-potassium pump. Now, these action potentials are propagated down axons or dendrites by alternating opening of sodium and potassium channels. So first, sodium rushes in. That's going to depolarize the next region, so sodium's going to continue to rush in. And in this area, once depolarization gets high enough, potassium is going to start rushing out. So you get this cycle of sodium and potassium that moves down the neuron towards the nerve terminal where we're going to connect with the next neuron. I'm going to show some videos and we're going to look at what this action potential propagation looks like in class on Monday. We'll also put all of these signaling pathways in context by talking about how they play a role in apoptosis. So if you have any questions, please feel free to shoot me an email, and I look forward to seeing you guys on Monday. I hope you have a great weekend.